Okay, here we're going to look at a hypothesis test where we have two samples and we're looking to compare the two samples. So we don't have a one sample test where the null hypothesis is going to be the population value is equal to this. Now we're going to see, are the two samples different from one another? So we're not comparing one sample to like a theoretical value. We're comparing two samples together and saying, are they different? Are the two samples statistically different? And so the data we're looking at here is from the NBA. So we have the Boston Celtics, Oklahoma City Thunder. This past season, the two highest point differential teams, so point differential is the difference between that team's points and their opponent's points. So the Celtics were 11.3 points per game better than their opponents. The Oklahoma City Thunder were 7.4 points per game better than their opponents, which seems like a fairly significant margin. And so you could ask the question, are the Boston Celtics statistically, this sample, a different true population mean than the Oklahoma City Thunder would have? Or are the two values close enough that it's likely that if the two teams were equivalent, they would possibly get values this different? I said that in a sort of convoluted way. I think it's written better here on the slide. Was Boston significantly better than Oklahoma City? Or could they be equal teams and this difference just happened by chance? So if we look at the box plots, it becomes a little bit more muddy of a picture, right? So 11.3 versus 7.4, yes, that seems like a big gap. We look at the box plots and we see that things are a little bit more closely matched, right? So the average value on these box plots is indicated by the X. And yes, Boston is up here, Oklahoma City is a little bit lower, but in the box plots, the Thunder spans a larger range. The Celtics spans a slightly smaller range, but they both have fairly high values and a lot of overlap in their box areas here. So it's a little bit harder to discern from this that one team was obviously better than the other. Okay, so now if we look at it by bar graph, we get a little different view of this. Now we're just taking the mean value, and I've plotted here error bars that represent the standard error. So you can see how much standard error there is in this average value for both teams. And then you can see that there does look to be a bigger gap here between the two teams. And the summary data is over here. We have the means, 11.3, 7.4. The standard deviations in the samples, 15.6 for Boston. Oklahoma City was a little bit larger, as we could tell in the box plot, 17.4. And then their standard errors, 1.7 and 1.9. That's what's indicated by the error bars here. But that doesn't tell us the answer to the hypothesis test. We do need to do a little bit more calculation to see if there's a statistically significant difference there. And so what we need is the standard error in the sampling distribution for the difference in the means. And to calculate this, we use the formula here. So this is the standard error. So sigma always is going to represent standard error about that mean difference. And the way you add the square of the other standard deviation and divide by that sample size, and then you take the square root of the whole thing. So we need to calculate this number and then calculate the t-score. And the t-score is the mean difference in the samples minus the null hypothesis, what should the mean difference be? And typically in these cases, your hypothesis is that they're the same and you're testing if there's a difference. In in theory, you could test if like one team was 5 points better than the other. But that would be fairly unusual. Usually you're testing if the two values are the same. So this part is normally just 0. So we take the difference in the means and divide by the standard error that we get from this formula. And then we get a t-score and proceed just as normal. Okay, so from this calculation, you can see I've plugged in the values from previous slides. The sample size is the number of games they play. This is their standard deviations. We get value 2.6. You take the difference in their means, divide by 2.6, get 1.5 for the t-score. Plug that into your t-distribution calculation from Excel, and that gives us a p-value of 0.07. Now you notice the t-distribution actually gave us a value of 0.93. Because this value is on the right side of the peak, and we get the left tail probability, we want the area on the right for our p-value in this case. And so that's a 0.07, which is slightly greater than an alpha of 0.05, so we can't quite reject the null hypothesis here. Maybe with more data we could. It certainly would warrant taking a little bit more data when you're that close to the p-value, the criteria for the p-value, but it's not below, so we cannot reject the null hypothesis in this case. However, I want to mention that there's an easier way to get this, and more commonly when you have two samples, you can just use the t-test function. So we did quite a bit of calculating here to get to this answer. We've taken mean values, standard deviations, found standard errors in the samples, and then to do the hypothesis test, we need the standard error in the mean difference. We got to plug into this formula, find the t-score, and so we did a lot of calculating to get to this answer, eventually plugging into the Excel t-distribution function, subtracting from 100. A lot of steps. Normally, we don't do analyses like this for comparison of two sample means. Instead, we let software do the work for us. And in Excel, there is a t-test function. And that's what we've essentially done here is a t-test. We've used the t-distribution to test the difference between two population means. That's called a t-test. And the way you do this is you have the sample 1 data. So sample 1 data is what we're calling array 1. And you have the sample 2 data, that's array 2. So you would highlight sample 1 data, then highlight sample 2 data, and then here you put in a 1 or a 2. If you want the one tail probability, like your hypothesis that it's greater than or less than, you put in a 1. If it could be either, you plug in a 2, and it really just doubles the probability. There are different types of tests that make assumptions about the variance. In this case, we would just use an unequal variance. We don't have any reason to think that the variances are necessarily equal, so we would use an unequal variance. And we don't have paired data here. Paired data refers to when the two samples come from the same subjects. So maybe if we were looking at season 1 versus season 2 of a team's performance, then it would be paired. In this case, it's not. Okay, so if you plug this into Excel, we get a very similar answer. We get a p-value of 0.065, so still above the criteria, the 0.05 criteria, so we still would not be able to reject the null hypothesis.